All right, welcome to Module 3, a new module, new chapter, Chapter 11. A lot of Chapter 11 is very deep in numbers, a lot of concept, a lot of equations as well. So I highly recommend you go over the slides before going over this. I want to remind you that this is a supplemental visual for you guys, just so you see where the numbers are going, where we're picking it from, and such. But if you're not understanding, well, I mean, I'll try to do my best to explain it, but there's going to be some things where I'm just going to assume that you should already know. So we'll go ahead and see how we uh, interpret and understand this as far as we can, right? Starting off, number one, isotonic sodium chloride contains 0.9% weight to volume sodium chloride. If the E value of boric acid is 0.52, calculate the percentage strength of an isotonic solution of boric acid. So we're seeing this, and based from everything that we learned so far, E value is the new concept here, right? So for looking into isotonic solutions and such when calculating different parts to make an isotonic solution, the best way to go about it is to make all components equal to one category. And so for isotonic solutions, that's making everything equal to a sodium chloride equivalent. To do that for different drugs like boric acid, for example, we convert the amount that we have of our boric acid using a E value to find out its equivalent sodium chloride amount. So again, that's something that I recommend you go over a little bit more if you don't get that from as far as I explained. But math-wise, the equation to convert from the amount of a drug to its sodium chloride equivalent is, let's just say grams of drug, for example, times its E value. Not the website. So grams of drug times E value equals grams of NaCl equivalent. All right. So I see this. A hint for me that I'll give to you guys is we can make another pyramid like we did with specific gravity. So I'll show that to you guys real quick. So grams of drug, you're multiplying that by the E value, right? So E to get an NaCl equivalent. And so that way you're able to visually see what you need to multiply or divide to get a certain answer, right? And that's going to apply to this question right now, actually. So let's see that here. So we're given the amount of sodium chloride already in the form of a percent strength, right? And we're also given our E value. What we're calculating is the original drug. So amount of NaCl, E value, you're dividing. NaCl divided by E value equals your amount of drug. So these are both, we're given a percent strength and they're asking for a percent strength. So 0.9% is, remember the way that I extract this is 0.9 grams per 100 ml. Okay, so let's just take out the 0.9 grams from that, from knowing that, because we're going to end up with something over 100 ml anyways. That's how we determine our percentage strength, right? So we can take that. So 0.9, and so that's our amount of NaCl divided by our E value, which is 0.52. Okay, let's do that real quick. 0.9 divided by 0.52. Just for the sake of writing it out, say 1.73 grams, right? And we know that that's going to be 1.73 grams over 100 ml. So that's going to be 0.0173 grams per liter. And then they want that as a percentage strength. So you want to multiply that by 100. That's how you get 1.73%. So that's the percentage strength of an isotonic solution of boric acid. Um, that's just I'm just wrote it out. I just wrote it out like that to show you how what's going on when calculating this. You could have just divided this by that to get grams per ml as it is. Divide that by the e-value to automatically get this answer, and then multiply it by 100. But this way, you're seeing each step and you're understanding each step. To each their own. Okay? But that's your answer. 1.73%. Okay. I'm gonna keep that up there, so it's probably gonna come in handy later on as well. Okay. Let's do number 2. Number 2 wasn't a homework problem, but I feel like the idea of freezing points should be something that we should cover a little bit, just because they weren't in the slides, and it's this topic is a lot more chemistry based, so it's just something good to know, just in case, right? So reading off the question here, a solution of anhydrous dextrose contains 25 grams in 500 ml of water. Calculate the freezing point of the solution. Like I said, a lot more chemistry based. Different ways to go about it, but an equation that we can typically use in this scenario is TF, or delta TF in that case, equals I times KF times M. Okay, so let's just describe each factor right here, right? So TF is our freezing temperature, or changes to freezing temperature. I here is, just by name, it's called the Van Hoff factor, but it's just telling you how many particles there are in a solution once dissociated in water. So for NaCl, for example, if 100% of the amount of NaCl put into water dissociates, then there are 2 parts of NaCl, right? There's 1 part Na, sodium, 1 part chloride. That's what the I factor is. And to get that 2, you need to also make sure you say that 100% of this salt dissociates and such. We'll get into that later, right? Later questions. For dextrose, dextrose isn't something that dissociates in water. It just stays intact once put into water. So that factor is just going to be 1. It's just 1 part of dextrose. Kf is the, lack of better words, the depression constant. It's just a constant number that tells you that for every 1,000 grams of solvent, this solution will decrease the temperature by this amount of degrees. So for water, and then this is a value I highly recommend you guys memorize, just because that water will probably be a constant solvent for a lot of these questions. The constant for water is 1.86. 1.86. It's just something for you guys to remember, right? And then M. M is molality. Molality is MOLALITY. The units for that is moles per kilogram. Okay? So that's what's really, and that's molality is used to cancel out the units for the constant, the depression constant. Not the constantly depressed, but the depression constant. A bad joke. Anyways, so we need to solve for these and then multiply together to get our depression or our freezing point. So we already know I, like I said. Um, I is 1 because dextrose does not dissociate in water. Kf, we also know because the solvent is water. The constant for that is 1.86. If it were another solvent, they should provide the Kf for that if solving for an example like this, right? And then molality. So molality, remember, is moles per kilogram. So we need to find moles, and then we need to find the kilograms of solvent. Moles of something per the kilogram of solvent. So we have our grams here, grams of dextrose, and we have our molecular weight. So it's 180 grams per mole. So we have what we have, and then what we want is moles. Conversion factor is the molecular weight. 25 grams times 1 mole, 180 grams equals, take a look here, 25 divided by 180. Sake of writing, just put 0.14 moles. And then we're given ml of water, right? We should know by now that 500 ml of water equals 500 grams of water. Why though, right? So to find grams of something from the volume of something, the ml of something, we use density, grams per volume, grams per liter, grams per ml, typically grams per liter. So 500 ml of water is equal to 0.5 liters, and then 0.5 liters is equal to 0.5 grams. So, sorry, grams per liter, 0.5. Yeah, grams per liter. So 500 ml, that's equal to 0.5 grams. It's grams per ml. So there's 500 grams in 500 ml. I know. See, like when numbers go around, it gets a little bit more confusing. 500 grams and 500 mLs of water because the density is 1 gram per 1 ml, right? So there's 500 grams. We need to convert grams into kilograms. So 500 grams divided by 1,000 equals 0.5 kilogram. So I'll just write it out here. 500 ml equals 500 grams equals 0.5 kilograms. All right. So our units for molality again was moles per kilogram. So we can do this, 0.5 kilogram. I can equate it, but I can also just put it right here as its divided form and then calculate it all together. Okay. So all we got to do now is multiply it all together. 1 times 1.86 times, in parentheses, 0.14 divided by 0.5 equals 0.52. Let's just write it here. 0.52 degrees Celsius. Now that is our change in freezing temperature. they actually want to know the actual freezing point. So you just subtract that from 0. 0 minus 0.52. Cool. So that's the general idea of uh, freezing points. You just need to know, what each of these factors are. So then you can later on for different questions, they may need you to isolate different parts, and you know what you are isolating because of this equation now. So hopefully that wasn't too confusing. I also remember now that there are 500 grams of water in 500 mLs. All right. Number 3. Okay, so now we dipped our toes into freezing water, haha, let's get into number 3. This is a homework problem. Freezing point of a molal solution of a non-electrolyte is negative 1.86. What is the freezing point of a 0.1% solution of a zinc chloride with a molecular weight of 136 grams, dissociating 80%? That's very important, dissociating 80%. Remember how I kind of like vaguely talked about dissociating 100%? Um, we'll get more into why that's important. And then for lack of more definite information, assume that the volume of the molal solution is approximately 1 liter. Okay. So there's different ways to go about this. I'm going to show you my way because I'm the one teaching, and fair thought, I think this might be a little bit easier. So let's go about it. You have all these factors here to write about to find the freezing point of zinc chloride. So don't exactly worry about the molal solution of a non-electrolyte because the I factor for that is going to be different for the I factor of zinc chloride, which is a salt that can actually dissolve in water. So don't exactly worry about that right now. So our original formula, right, freezing point, delta TF equals I times KF times M, right? Okay, so molality, molality is moles per kilogram. We're given a percent of zinc chloride in a solution. So 0.1% equals 0.1 grams per 100 ml. So let's convert that so we can find out how much total zinc chloride there is. 0.1 per 100 grams per ml. And there is 1,000 or yeah, 1,000 mLs or 1 liter of the solution. So we can cancel that out here. That should equal that plus 10. It should be 1 gram zinc chloride. Okay. And we need to convert that to moles now, right? It's moles per kilogram. So for every mole, there is 136 grams of zinc chloride. And that equals, do that real quick, divided by 136. Okay. Just for writing's sake, 7.4 moles. Okay. Now we need to find kilograms of solvents. When it's not specified what the solvent is, we assume that it's water. That's just something to think about, right? So 1 liter, that's 1,000 mLs of water. 1,000 mLs of water equals 1,000 grams of water, 1 to 1, right? And 1,000 grams equals 1 kilogram. So it's this amount of moles over 1 kilogram of solvent, which is the same thing, moles per kilogram, right? So we have our molality. That's good. And we just said that we assume that our solvent is water. So therefore, our Kf is also going to be 1.6. All we need to find out now is our I. So this goes back to that dissociating 80%. I'm going to give you guys an example here. So NaCl, right? If 100% of NaCl dissociates in water, that means that there's going to be 100%, or let's just say 100 parts, 100 parts of Na and 100 parts Cl. So how many parts total now, or dissociated parts total? There's 200 parts over our original like dissociation, like so 100 of NaCl, the compound itself. So for every 100 NaCl, if it's 100% dissociating, it's 100 parts Na and 100 parts Cl. And then once we divide this is how we get our I factor for 100% dissociation. Now, this is saying 80% dissociation. So there's going to be some additional parts to this. If 80% is dissociating, that means 20% or 20 parts is not dissociating. So 20% stays as NaCl. And then 80 parts is an NaCl that will dissociate. Then so we can branch these off, right? And that becomes 80 parts Na, 80 parts Cl. Okay? And now when finding our I factor, there's how many particles or parts are in the solution total. There's 80 parts Na, 80 parts Cl, and 20 parts of NaCl. 80 plus 80 plus 20, 160 plus 20 is 180. Over the original 100 parts, you get a I factor of 1.8. So that difference is very important. You don't want to be drawing trees the whole time during your exam, right? So the easiest way to go about it is for a compound that is 1 to 1, that means there's 1 part of Na, 1 part of Cl, for example. If it's dissociating at 80%, for example, it's going to be 1.8. The I factor is going to be 1.8. And then for every additional part of the compound, so zinc chloride, for example, there's zinc and then 2 chlorides. So that's 3 parts. For every additional part added to a compound, you increase that I factor by 0.8. So let me just write it out to show it to you guys. Zinc chloride. There's 2 chlorides and 1 zinc. So it's 1.8 plus an additional 0.8 because of the additional chloride. So our I factor is 2.6. And then it continually goes up by 0.8 for every additional ion, for to say, right? Okay, so now we know what our I factor is. All we had to do is just multiply everything together, right? So moving down here, 2.6 times Kf of 1.86 times our molality right here equals, just multiply that by 2.6 times 1.86. Okay. So that's the answer that we get for the change of freezing temperature, 36 degrees Celsius. So they're asking for the actual freezing point, 0 minus this, 0 minus this, getting lazy, 0.036. So it's the freezing point of a solution with 0.1% zinc chloride is negative 0.036 degrees Celsius. So not too far off from the freezing point of 0. Okay, so that's how you solve that. Puts a lot of concepts into play, right? There is freezing point, and that's why we talked about that in number 2 first. And then also talks about dissociating at percentages for the I factor. That's also another thing that we wanted to go about real quick. So that's number 3. Okay, so number 5 is an RX prescription, and it consists of anhydrous dextrose at 2.5% of the total solution. So we need to find out how many grams that is. There's a certain amount of sodium chloride that needs to be found out that is added to make the solution isotonic. We need to find out how much sodium chloride that is. Just based off the QS, we need to know that. QS is quantity sufficient. And then sterile water for injection is also added as directed, AD, for a total solution of 1,000 ml. Now the question asks how many grams of sodium chloride should be used in preparing the solution. We already knew that from the QS. So how do we go about this? You see when, and the label says isotonic dextrose. That should be like our cue to say, okay, we're going to be dealing with equivalents with sodium chloride. Because to make something isotonic, you want to make all these different factors equivalent somehow so that you're able to add, subtract, divide, and such, and then find what you want, and then return it back to its original form. So we're gonna do that. First, we need to find out how much dextrose there is in this solution, because we're only given a percentage of it. So 2.5% is 2.5 grams per 100 ml. And then times that by 1,000 ml to get the amount of drug in there. That's 25 grams of D, dextrose. So we have our amount of dextrose. We now need to find out, can you guys see that? Yeah, you can. Okay. We have our amount of dextrose. We need to find out how much NaCl that equals. So that's where we use our E values and such. And so you might ask, like, are we multiplying? Are we dividing? That's the whole point of the pyramid, right? We have a grams of a certain drug, and then, but according to this pyramid, we need to multiply by the E value to get the NaCl. So we need to find out what the E value is. Thankfully, we are given a chart. And according to this chart, for anhydrous dextrose, by the way, we go down here, dextrose. See how it says it's anhydrous and this dextrose H2O. So it's dextrose that hasn't been dried out yet. That's what that dextrose H2O means. Anhydrous means it's already dried out. So the E value, NaCl equivalent, for anhydrous dextrose is 0.18. So we can go back to our original problem here. So to find the NaCl equivalent of dextrose, 25 grams times 0.18 equals, do our calculator there, 25 times 0.18, 4.5. I'm just going to say NaCl and then EQ in the bottom for equivalent. So we know now how many grams of NaCl are equivalent to dextrose. So we have, those are the parts of the solution now. We have the other parts figured out. Now we need to find out how much NaC, and then we need to find out how much sodium chloride there is in the total solution, because that's how we isolate the amount of sodium chloride that needs to be added. So we are given that. So that's 1,000 ml. And then in an isotonic solution, that's what we desire, there are 0.9 grams per 100 ml. So let me just write that out, right? In an isotonic solution, there are 0.9 grams per 100 ml. In the slides, you might have seen that in different ways. You might have seen it as 9 grams per 1,000 ml. You might have seen it its fully divided form as 0.009 grams per ml. You can write it out any way you want. I just write it out like this because it's easier for me to recognize it as a percent later on. So, so now we need to find out the total amount of NaCl and the total solution. So it's this conversion factor times 1,000 mLs. Okay, and that's 9 grams. So there are 9 grams of NaCl equivalently in the total solution. So everything's NaCl except the amount of sodium chloride that we need to add to the solution, right? We can find that out now that everything equals NaCl. We just subtract 9 minus 4.5 equals 4.5 grams of NaCl. Okay. And the question is asking how many grams of sodium chloride should be used. So we have it in grams. That's it. That's literally it. Um, if it were, let me just show you, like, give you guys alternate scenarios, right, for prescriptions. They might say QS of, boric acid, for example, right? You do this whole thing with finding the equivalence, subtracting, but then you had to convert it back to its original drug, the quantity of its original drug. So you have this, the equivalent amount in NaCl of boric acid, for example, divide that by its E-value to get the amount of boric acid. But this is already as sodium chloride, and that's what we're looking for. So we don't have to do anything else with that. It's pretty straightforward. Hopefully you guys are making sense of what I say, what I got. All right, next problem. We're gonna skip a couple problems here. We go straight into number 9. Oh, how about that? It's just what I was talking about. Okay. So this prescription, tetracaine hydrochloride, there's 0.5% of the total solution. Um, a solution of epinephrine bitartrate at a ratio of 1 to 1,000, okay, is, there's 10 mLs of that. And then we need to add a certain amount of boric acid to make it isotonic. And then into purified water, there's a total solution of 30 ml. And then the prescription says make it an isotonic solution, and it's for eye drops, yada, yada, yada. The solution of epinephrine bitartrate is already isotonic. So, already isotonic, we don't need to use an E value in that case, right? Because we already know that it's an isotonic solution. So, what do we say about isotonic solutions? In isotonic solutions, there's 0.9 grams of NaCl per 100 ml. We already have that conversion factor. So, just remember that. How many grams of boric acid should be used in compounding the prescription? Okay, so let's solve individually and then isolate and find out our other answer, right? So same as before, 0.5% of tetracane hydrochloride, 0.5 over 100 grams over ml times 30. Okay, so let's find that out. 0.5 times 30 divided by 100, 0.15 of, I'm just going to say THCl. So that's how much tetracane hydrochloride there is. We need to find its NaCl equivalent, right? Because that's how we isolate for isotonic solution. So go back to our chart. Remember that it's tetracane hydrochloride. And our E value is 0.18 again. So we have our grams of drug, multiply that by our E value. So multiply by 0.18 to get an answer of 0.027 grams of NaCl equivalent. So let's just write that right there. 0.027. All right. So there we go. Now we have a solution of epinephrine bitartrate. Again, it says that it's already isotonic. So the only conversion we need is just the amount of NaCl in an isotonic setting, which what we said earlier was 0.9 grams per 100 ml times, there's 10 mLs in that solution, equals, you're dividing that, 0.09 grams of NaCl EQ. 0.009. Let me just make sure I multiplied that right. 0.9 divided by 100 times 10. Yes, we did that right. Okay. And then total solution. Total solution is also expected to be isotonic. So we do the same exact thing like we did with epinephrine. So 0.9 over 100 ml times 30 ml. So want to say 0.27 grams NaCl EQ. Right. So same as before, we have our parts calculated equivalently, and then our total calculated equivalently. Now we just subtract to find what's desired. 0.27 minus 0.09 minus 0.027. 0.27 minus 0.09 minus 0.027, 0.153. 153 grams of the NaCl equivalent of boric acid. But now they're asking how many grams of boric acid specifically, right? So this is the equivalent of NaCl to boric acid. So that's this guy at the top. Now we need to use our E value to convert it back to boric acid. So we find that E value for boric acid, and it is 0.52. We can do that here. 0.153 divided by 0.52 equals divided by 0.52. And answer for that is 0.294 grams of BA, boric acid. So same process as before, that last question that we did. We're just adding that last conversion factor because we're not looking for added NaCl now. Boric acid is being added. So we need to convert it back to the amount of boric acid. Okay. That's 9. Next question is number 12. Okay, so using the values from in the table provided, using the E values in the table provided, calculate the number of milliliters of water required to make an isotonic solution from 0.3 grams of the following: chlorobutanol, ephedrine sulfates. Okay, yeah, no worries. So we're using E values, and then let's do A first, right? Let's just write it out. So for A, there's 0.3 grams of CBT, chlorobutanol. Let's just shorten it out for now. And so we need to make it isotonic. We need to make it at an equivalent first because we're not as stated that it's not stated that it's already an isotonic form, right? So grams times E value. We need to find the E value of chlorobutanol. Chlorobutanol is 0.24 times 0.24. Okay. And then for B, ephedrine sulfate, shortened out. E value of ephedrine sulfate, 0.23. Okay. So we just multiply those out. Point 0.3 times 0.24, and then 0.3 times 0.23. So 0.069 grams and then 0.072 grams. And those are the equivalents, the sodium chloride equivalents of those respective drugs. Now they want the number of milliliters of water. So to make it an isotonic solution. So we have these equivalents, and then we think like, what's one way that we could find the amount of water used in an isotonic setting, right? We have our equivalents now in as NaCl. If you remember back, that conversion to find the amount of NaCl in an isotonic solution, right, was 0.9 grams of NaCl per 100 mLs of water. That's how we find it. So we're gonna erase that first part right here. I could just, you know what, let's just do this. So yeah, I'm just gonna multiply it right here. So we have grams of this, and it's 0.9 grams of NaCl per 100 mLs water. So we just flip that out to get water. That's what we want. 100 ml divided by 0.9. Same goes here. 100 ml over 0.9. And then we get, let's find out. So 0.072 times 100 divided by 0.9 equals 8. And then checking this one times 100 divided by 0.9. 7.6. Okay. And it's in ml, so let's just do this. Again, it's not specified in sig figs and such, but make it look nice, right? So that's how much ml there is for each of the respective drugs. So it's not very expansive concept-wise. You just need to know certain things, certain foundations, and then just know when to pick it off. All right. This is, okay, 12. We have one more problem for this chapter before we head on to the next one. And that is 15. Just because this chapter also includes buffers, I wanted to quickly add one as well. I know it looks like it's totally random. It's way off from what we were doing before, but I told you, like, I wanted to consider all topics. So let's get right into it. What is the change in pH on adding 0.02 moles of sodium hydroxide to a liter of a buffer solution containing 0.5 m's of sodium acetate and 0.5 m's acetic acid? The pKa value of acetic acid is 4.76 at 25 degrees Celsius. Okay, so we we're looking for a change in pH. We're given a pKa, and then these strengths of an acid and the salt that is formed from that acid. Okay, and then what's changing the pH is that base, sodium hydroxide. So let me just write it out for you, but I wanted to explain that because the equation that we will be using for this problem is, if I remember right, it's called the Henderson-Hasselbalch. But the equation goes pH equals pKa plus the log of concentration of the salt over concentration of the acid. Okay, so I recommend just memorizing like this equation, because if they're asking you to find the pKa, you just have this memorized, and then you subtract this whole thing to this side. So instead of just trying to remember both equations, right? It's just easier to just think, okay, this equals that, and then move it around. Because then you might get confused which is minus and which is plus, right? So let's go ahead and fill in what we have. So we have a pKa of 4.76 plus log of what are our concentrations? So okay, so 0.5 m of sodium acetate and 0.5 m of acetic acid. So acetic acid, that's the bottom. So top is the sodium acetate. That's our salt. So it's 0.5 over 0.5. Now, that would be to find out what our current pH is right now. All right. But we're trying to find the change in pH, right? So that's one change in pH once a certain amount of this base is being added into this buffer solution. So again, this conceptually is chemistry based. So you need to just think like when you're adding a base into a buffer solution containing an acid, what is happening, right? So when you're adding base into that solution, you're um, creating more salt, and the and then the acid is being neutralized. So there's going to be a lesser amount of acid. Hopefully, like that. If you need to like go back into like titrations and such and buffers, but that's the idea, right? You have an acid within a buffer. Um, when a base is being added into that, there's base is neutralizing the acid, so there's going to be less acid, and then because from that reaction, more salt is being formed. So in that case, there is going to be from those that zero point 0.2 moles of sodium hydroxide, you are adding 0.2 more, is it 0.02 more into the solution and subtracting 0.02 into the solution. Okay, so now all we have to do is calculate this. Right. So that is 4.76 plus the log. Where is the log? Right here. So log, and then use parentheses. You can use however many parentheses you want, as long as you're closing them right. So our numerator is 0.05, sorry, 0.5. 0.5 plus 0.02 over 0.5 minus 0.02. Close that. And then, so the pH, once that amount of sodium hydroxide is added, is 4.79. Okay, so we get that, but that's not what the question is asking for. What is the question is asking for the change in pH. So we see it increased, so 4.79 minus 4.76 equals 0.03. You could say pH units. pH units. So yeah, that's what you need to understand about buffers and such. But this equation is very important, and then from there on, you manipulate. That's the basis for this class, at least. All right, and that is the end of chapter 11. Um, we're going to move on to chapter 12, and then that's going to be last chapter 12 for module C, and then we'll move on to module D, and we'll be done. All right, see you in the next one.